Good morning. My name is Marina Chirija, and I'm going to be presenting to you a project. I'm going to take you through the introductory bit of the project. And our project is about an adaptive elementary education system. Well, these are our contents of the presentation. And we're going to first look at the background and introduction. So in the background and introduction, we are basing on in the current world, in the current country, they assume that all students can learn at the same pace, which is quite different because students learn at different paces. And the system is there that can recommend for them, okay, do this, maybe you failed here, go back and learn this, that will be good for them. So that's the problem that we're going to call the one-size-fits-all problem in regards to this project. So to solve this, we are looking at implementing 4 techniques. That's the raft, which is to collect information from the external data sources. Then we're looking at GPTs that will help us understand and generate human-like text. We're looking at ML-D and ML-U, which will help us understand the student's input and generate the human language. So people have already implemented these things, but in the different sectors. There is shopping, there is entertainment, and these are trying to recommend things for you to buy or watch based on whatever is being searching. But first, we're looking at recommending for you something based on how you've been performing your learning phase. So these are the things that are related. So the way they have implemented the things of recommendation, that's we are trying to look at it in that way of recommending, but in this case, based on your performance and everything. So the domain problem, as I've already mentioned, is called the one-size-fits-all approach, where they ensure that everyone learns at the same pace, which is never the case. So the computational problems that we face are imbalanced data sets, and we managed to solve this using data cleaning, model interpretability, where I use the explainable AIs with techniques like sharp line and attention release. Yes, then we have called that problem, where it has written information to give you recommendations. Then we also have a few shot and 0 shot learning challenge, whereby in this case, it's learning from the little example that is given to it. So here we had to carry out fine tuning. Yes, and so when we're carrying out this, the research questions we asked ourselves: how can we dynamically have this content adjust to this model? How will these techniques actually help us with an adaptive learning system? And what techniques are most efficient in analyzing this? So the objectives we came up with after asking ourselves these questions were we want to design a generative model that will personalize the learning experiences, one that will enhance the student engagement, one that will ensure that the platform relies on dynamic content, and one that will neglect biases from the training data so that it can prevent unfair personalization. And when we carried out research from the different sources, we came up with a model that can enhance personalized mathematical learning using the RAG. We implemented an adaptive learning framework and also leveraged transformer-based models. Yes, thank you very much. That was my part. My group mate will start on for me and take you through the technical build.
Hey everyone, my name is Mrs. Eugene Faise. I'm going to be taking you through the data sets, experimental data analysis, and the model architectures as well as the demonstration. So in this case, we're using the GSM-8K dataset, that is a grade school math dataset that contains around 8,000 or more sample questions and answers, which are in terms of word problems. So we were able to conduct exploratory data analysis, which we were able to understand the distribution between question length and answer length, and also to view the distribution of the question types. Then we were also able to understand the answer length by math operation and say correlation between questions and answers, and also to identify the variation of the KDEs between the question and answer length and keywords in the questions. Then in our model, in our project, we're looking at a methodology where we're using the GPT transformer, which is the GPT Neo over 1.3 billion parameter, where we first tokenize our dataset questions, then we perform cross-entropy loss and optimize it using ADAMW, optimize it to create a fine-tuned model. So basically, this is our calculation. This is our calculation to view the learning rate over epochs, and also to generate a total number of epochs. So basically how our model works is we generate a text response when a query is put in our system, and it is generated in hand in hand with a preemptive prompt that is sent to a relevant information source that is put from the various knowledge sources. Then that retrieved information is going to be enhanced, and it is going to now be put into a large language model endpoint. Then we also were able to use vector databases that help us understand, whereby we send a query result, a query from our application into our embedding model that is sent to a vector embedding that is stored in the database, and then it will produce a query result. Then from our model we were able to come up with various results. For example, in our table we were able to evaluate our first 10 epochs and get their accuracies and the loss and their runtimes. We are also able to evaluate the evaluation loss in respect to the training loss, and also view the model evaluation metrics such as the BAT score, the ROG L, the BLUE, and the F1 score and perplexity score. Then explainable AI, where we're able to generate attention visualizations. For example, we're able to generate attention weights based on a sample question. For example, the question, as you can see here, a teacher has a teacher has 10 apples and she gives 3 to one student and 2 to another. How many apples are listed? So it will give attention weights based on how important each token in the question is pertaining to the question we have. Then model selection, we're able to generate only one model based on using the Elutha AI GPT Neo 125 million parameter language model, and the generative model sends results to users' input based on the preemptive prompt. Then we also have a phase query model that determines similarity of input questions with available sample questions. So we're using Streamlit that enables interface API and it uses GitHub Actions. Then to demonstrate, let me take you to our demonstration here. So basically, first of all, we have a phase query whereby we can put in a question and it gives us a response. For example, when I put what is the product of 5 and 17. So what this does is when I click apply, it will bring the top similar questions and show me the similarity indices of them. So we can see it has already produced the top similar questions and it has provided the similarity indices from them. Then similarly, we have the solve math problem model. So basically what this does is it creates a model based, we input a math problem, word problem, then to generate an answer. So when I say what's the product of 15 and 26 and we click solve, it will solve using the math model and generate an answer. So from this we're able to generate an answer using, whereby we are able to set the temperature and the maximum length of of the token. Then we are also able to view the debug information and be able to see what's going on. So that was all for the demonstration. So our IP assets, basically our algorithms, the learning processes, our source code and research paper, and fine-tuning processes. Then our limitations, these were the high computational requirements, whereby this model was needed a lot of RAM and a lot of system specifications, which were highly hard to get at this time. Then also we had hyperparameter sensitivity, graph size scalability issues, data limitations in terms of quality and availability, and data pre-processing complexity. So in conclusion, we have developed an AI-driven adaptive system that personalizes elementary education, implemented the method dynamically, adjusting content. Thank you so much. On to the next presenter.
Well, having gone through the previous bits of the technical bit, in our next steps, we're looking at having key improvements that we can enhance the effectiveness and bring more applicability. So in this case, we're looking at having more data sets that we can train on. We're looking at optimizing the retrieval process by refining the phase indexing and reducing the query latency. We're looking at expanding the data sets so that we can have more data to train from and have the model participating better. And then we also look at how developing an interactive web-based platform or a mobile platform that can help users to interact really with the system. Then in conclusion, our acknowledgements go to Mr. Mabin Kaliongo, who is a lecturer who has provided us mentorship and guidance in the coming up of this work, and he has been with us in every step to correct us, guide us, give us tips and share everything. We also give our acknowledgements to Mark Unipod that has given us the audience to showcase our business canvas and ideas, especially in the terms of monetization and scaling, and also give us tips on how best we can make it better and market it better. Then lastly, we also give acknowledgements to the IP office for securing our intellectual property and then advising us on how best we can get the rights. Yes, thank you very much. That was it from Group 15. Thank you.